சொல்லுங்க சார். PLC group ஆகும்.
சார் என்னோட வாய்ஸ் கேக்குதா?
கேக்குது மேம்.
தேங்க்யூ தேங்க்யூ.
Good evening, respected professors, academicians, research scholars, and students. A warm welcome to the 5-day online faculty development program on exploring the frontiers of computation, formal languages, and automata. It is our honor to have you all with us today. Ladies and gentlemen, it's our pleasure to begin day one of the faculty development program with our esteemed speaker, Dr. I. Vallirathi, Associate Professor, Department of Computer Science. Our focus today is on unlocking the intricacies of finite automata as we delve into the topic, unlocking deterministic finite automata from NFA. Let us begin with a prayer. I would like to invite Mrs. Chermakani, Assistant Professor, Department of Information and Technology, JP College of Engineering. Let us lead us in prayer. Please, ma'am.
Okay, sir. God, our loving Father, we thank you for this wonderful evening. We come before you today with gratitude for the opportunity to gather for this faculty development program. We thank you for the wisdom, knowledge, and experience you have granted to all the participants for the opportunity to grow and learn together. We ask for your guidance throughout this program that it may foster an environment of collaboration, innovation, and continuous improvement. May the resources shared here inspire and empower every educator to enhance their teaching and enrich the lives of the students they serve. Grant us wisdom and patience as we embrace new ideas, skills, and strategies, and help us to remain humble, open, and committed to our growth. We ask for your blessings on this program and may it be fruitful in advancing the mission of education and betterment of all those who are part of it. This we ask in the name of our Father, Lord Jesus Christ. Amen. Thank you.
Thank you, ma'am, for your thoughtful prayer. Next, we have Mr. N. Senthil Murugan, HOD, Department of Information and Technology, JP College of Engineering, who will deliver the welcome address. Please, sir.
Good evening, esteemed guests, respected colleagues, and dear participants. It is my privilege and pleasure to warmly welcome you all to this faculty development program, a platform dedicated to fostering excellence, innovation, and collaboration in academia. Today marks the beginning of an enriching journey where we come together to learn, share, and grow as educators and lifelong learners. First, I extend my heartfelt gratitude to our distinguished dignitaries for gracing this occasion. We are honored by the presence of our dedicated administrator, Reverend Sister Camlet, whose unwavering support ensured the seamless functioning of our academic endeavors. our esteemed principal, Dr. Rajkumar, whose visionary leadership continues to inspire our institution growth. Our 5 accomplished resource persons, Dr. I. Vallirathi, Associate Professor, Department of Computer Science and Engineering, Rohini College of Engineering and Technology. Mr. R. Rajasekhar, Assistant Professor, Department of Computer Science and Engineering, Kalasalingam Academic of Research and Education. Dr. Nagarajan Kurusamy, Associate Professor, Department of AI and DS, Sri Shanmuga College of Engineering and Technology, Salem. Dr. K. Deeba, Associate Professor, SRM Institute of Science and Technology, Chennai. Dr. E. A. Muhammad Ali, Associate Professor, Department of ECE, JP College of Engineering, Tenkasi, who bring a wealth of knowledge, experience, and expertise to guide us through this program. To our passionate participants, faculty members from varied disciplines, your enthusiasm for professional growth is commendable. This program is designed to empower you with cutting-edge academic strategies, research insights, and tools to navigate the evolving educational landscape. Over the next 5 days, we will explore into interactive session, thought-provoking discussion, and collaborative activities aimed at enhancing teaching excellence and student engagement. A special thanks to our resource person for dedicating their time and expertise to this initiative. Your contribution will undoubtedly leave a lasting impact on our faculty community. Once again, welcome to all. Thank you.
Thank you, sir, for your warm welcome. Now I kindly invite Dr. Armstrong Joseph, Associate Professor, Department of Computer Science, JP College of Engineering, will introduce the session. Please, sir.
Yeah, good evening, one and all present here. So I am Dr. Armstrong Joseph. I am going to introduce about this faculty development program, which is already orally explained by our HOD IT. So even though I want to give you details about the program as well as today's session. So let me show that my small presentation over here. Sir, so good evening. It's my pleasure to welcome you all to this second FDP course on exploring the frontiers of computation, formal languages, and automata. I'm thrilled to welcome you all to our faculty development program, which is arranged by our college. Today, we are diving into the fascinating world of automata theory. I'm confident that this FDP program will equip you with valuable insights and practical knowledge that you can apply in your teaching and research. Finite automata forms the backbone of the formal language theory and computation model, serving as foundation for compiler design, text processing, and even cybersecurity applications. One of the fundamental transformation in automata theory is the conversion of NDF or NFA into Deterministic Finite Automata, that is NFA to DFA. It not only simplifies the state transition, it enhances the computational efficiency. Let us embark this journey to faculty development by this program. So about this FDP course, it explores the integration of multiple disciplines within the computer science and engineering. Right now it's evolved in various fields like ADS, and artificial intelligence, cyber securities, which is the fundamental to these multiple discipline integrations. And embracing knowledges from automatic theory, such as computational theory, AI, cybersecurity, is all involved in this automata theorem proving. Students and researchers will learn innovative ways to approach challenges while designing, analysis, and genetic programming. Everyone knows very well, automated theory is the fundamental tool of computer science because theoretically we derive all the patterns to accept or not. From that patterns, we learn something which is used in our artificial intelligence. Like in previous information as given our HOD IT, this is a schedule. So what is the course outcomes? We talk about these outcomes, the interdisciplinary approaches and emerging technologies which are available in our multidisciplinary activities. Similarly, collaborative across the disciplines and then conducted research. These are the outcome of this FDP course. So let us see the introductory about the first day sessions. In the first day focuses only the unlocking DFA, that's the Deterministic Finite Automata, from non-deterministic finite automata. From NFA to DFA, we unlock, it means that we can derive this automata. So this session aims to provide faculty members with deep understanding of the conversion process, theoretical underpinnings and effective ways to teach the concept of students. This session objectives: first, strengthen the theoretical understanding because there is this one. Second one, enhance the teaching methodologies. So there's a pedagogical strategies for teaching automatic theory. There's various methods available to teach the students. They learn from us and then they can use the aids from internet, like various tools. And hand-on practice, the problem-solving methods. So many methods are available to solve the problems. For example, practical exercise can be given to NFA to DFA, and then curriculum integrations. Whatever we learn from this FTP, that we can integrate with the existing curriculum. And similarly, research and innovations, the latest field like AI, cybersecurity, and text processing, that's natural language processing, can be used for our research and new innovations. Similarly, we can do research directions like real-world applications, like natural language processing, as well as knowledge-based systems from artificial intelligence. Similarly, cybersecurity. If we come under cybersecurities, we can utilize this like some pattern, detect the virus patterns, and we can get the lesser time. There's a lesser time to find out the intersections. So that is the one of the area we can develop this. So this can be used to be informed to our students to learn from these concepts. Similarly, as usual, question and answer, feedback. This is session outline. Today's session outline. First, they will explain the introduction about the finite automata and then how to construct this automata using some algorithms and DFA state minimization, and what are the methods we can teach to the students, what are the applications and research oriented. At last, question and answer sessions. Some automation simulator we can use like JFlap is nothing but you see in the next slides. Like next slides. Simulation like JFlap and automata simulators. GFLAP is the Java formal languages for automation package. So we can explain the concepts to the students using these packages so they can very clearly understand the concept that everyone knows. The latest applications also we can use, like normal reference material and online courses. What are the expected outcomes from this FDP? So gain understanding from NFA to DFA. For this particular session only I am talking. And acquire practical skills to teach automata theory effectively by solving problem solving techniques. And then equipped with the tools, techniques to simplify the complex concepts to the students, what we learn from this FDP and explore the opportunities for research. Finally, I want to conclude that this session, this is the first FDP session, that's the today's sessions, we learn or the resource person will give the information to us and how to unlock DFA from NFA. It's the bridge gap between the theoretical knowledge and practical teaching methodologies. By empowering the faculty members with advanced skills, innovative teaching strategies, the session aims to enhance the quality of automatic theory educations. I welcome this session's resource speaker, Dr. Vallirathi from Rohini College of Engineering and Technology. She is the associate professor working there. She has so many achievements like publishing papers, international paper, journals, 4 numbers, national journals, 2 numbers. She presented and attended conference like international versus national, each 4, and she has the domain area, wireless sensor networks and compiler and computational programming languages, web design. Basically, she very well experienced in theory of computations. We welcome her to deliver related to this, like today's topic, unlocking DFA from NFA. I am welcoming ma'am to deliver this session. Thank you.
Thank you, sir, for your brief intro about today's session and introducing our speaker. May I request all participants to kindly mute your microphones during the chief guest presentation to avoid any background noise and ensure a smooth session. Thank you for your cooperation. Now let us move on to the session, which will be presented by Dr. I. Vallirathi, Associate Professor, Department of Computer Science, Rohini College of Engineering and Technology, Kanyakumari. Please, ma'am.
Thank you, sir. Okay. Good evening to all. Are you hearing me? Shall I start question, sir?
Yes, ma'am. Yes, ma'am.
Okay. Good evening to all. I am Dr. Vallirathi, Associate Professor of CSE Department, Rohini College of Engineering, Kanyakumari. Really, I am very happy to present in this session. Here, in this sessions, we are going to discuss and learn about unlocking deterministic finite automata from NFA. So actually, finite automata is a machine. It is used to recognize the patterns. That is, a machine or model. It is used to find the string is accepted by the machine or not for all possible inputs. So the behavior of a machine is captured for the all possible inputs in the finite automata. So it accepts or rejects the input based on the predefined input sets or the strings. The machine is defined based on predefined input symbols or strings. So this collection of strings are known as language of automata. So normally finite automata model is used for modeling communication or network transformation protocol and digital circuit design. At the same time, check the behavior of a machine. So in this our closely used one of the application is compiler. The compiler is a translator. It translates one language, that's a high level language, into machine language. It has collection of phases. Actually, 6 phases are available. So the first phase is a lexical analyzer. So the purpose of lexical analyzer is it recognizes the pattern. So example, imagine the high level language is an int is a C programming. So here the declaration statement is int a and semicolon. So we declare one variable a. Okay. So that format is int a semicolon. So here the lexical analyzer identify int is a character. Int is a character and a is a identifier. Semicolon is a punctuation symbol. So here this int int is a keyword. So that can be recognized or identified by the automata. At the same time, the variable a is an identifier or variable. So it can be identified by the automata. So what is the pattern for the keyword? Int is int. So the starting state must have I. Then the next state have n. The last state is in T. So like that, what is the pattern for the identifier? A letter followed by a letter or digit. So actually the identifier is defined by a letter or letter followed by a digit. That's a mark 1, mark 2, like that. This is a variable. So the pattern or the automata is defined by the starting state is a letter. Then if it has more than letters or digits sometimes, otherwise it may directly move to the final stage. So that is an automata for the identifier. So actually automata is says yes or no. So that can be represented by the mathematical model. It has the collections of tuples or components. The first one is stage. That is an S. Then input symbol is in sigma. And the transaction functions between the states that is defined by the del. And initial state is an S0. Then the final state, that's an acceptance state, is an F. So actually two types of finite automata, deterministic finite automata, non-deterministic finite automata. What is deterministic finite automata? Each state has a single transition for a single input. So example, we have here the 1 is an first stage. So it has single transition for an input A. No more transitions for input A. So exactly one edge leaving out for each symbol. That is a deterministic finite automata. So each state has a single transition for a single input. The non-deterministic finite automata, no more restrictions. So it has more than one transactions for input symbols. So then regular expressions. So the model is checked by a collection of input strings. Okay, so this collection of input strings is described as a language. So that algebraic representation is regular expressions. Example, so consider A is a simple. It is simple. So the regular expressions for A is a small a. So the language is L of A. So here it has only one string. That string length is only one. That is an A. So if it is an epsilon null transaction, means epsilon, no more data passed, but it has a make a bridge. So that is an epsilon. So the regular expressions for the epsilon is an epsilon. In the same way, the pi. So no more transactions. Okay, no more connectivity. So that is represented by the by. The state doesn't have any transition. That is pi. So in this induction's point of view, union of two regular expressions E1 and E2 is defined by E1 plus E2, and the concatenation is defined by E1, E2. Then the clean closure. So consider A is the one regular expression. So what is an clean closure? That is an A star. So consider A is an A. Only one symbol that can be generated by the automata. That is an A only. So A star, that is 0 or more occurrence of A. So star is indicated 0 or more occurrence of A. So here is star. That means A star. It creates epsilon A like that. So A star, 0 or more transactions. 0 is indicated as epsilon, then 1 or more. So in the same way, positive closure, that is an E plus. So consider E, a regular expressions. E is an A means A plus. That is an A like that. So here no more epsilon transactions because 1 or more. Plus is indicate 1 or more. Then we move to the transformations of DFA to DFA from the NFA. Actually, NFA is represented by two ways. NFA with epsilon and without epsilon. So in this first model, the conversions of NFA without epsilon to DFA. Then the second one is NFA with epsilon to DFA. So that can be transferred by using a subset construction method. Then finally, we will discuss about regular expressions to DFA. Directly we convert regular expression to DFA. So that's done by the direct method. So the first one is NFA without epsilon to DFA. So here, so the NFA without epsilon, I have one state diagram with three states, Q0, Q1, Q2. So here the Q0, it has initially one arrow. So this indicates this arrow line, this indicates this Q0 is the starting state of the state diagram. Then this double circle is indicate Qn is the ending state or final state of the NFA. Then it has all possible transactions, but no more epsilon. So that is an NFA without epsilon. Then the transition table is represented and generated by the input in each stage. So here 0 and 1, only the set of input symbols, only 0 and 1. The states are Q0, Q1, Q2. So here the Q0 has only one transition for the 0 input that moves to the Q1, and it has two transitions for the input 1. That transitions are Q0 and Q1. Then Q1 has two transitions for the input symbol 0, that is Q0, that is in Q1. Yes, move to Q0 at the same time Q1 For the input 0, it moves to Q2. So it has two transitions, but no more transition for the 1 in the state of Q2 also. So this is a transition table. So next, how to find the DFA? So that can be described by the following steps. So first one, transition function of DFA. So here, the starting state of DFA, our aim is construction of DFA. So the starting state of DFA is starting state of NFA. So actually, the starting state of NFA is Q0. So I take directly, okay, Q0 is a starting state of the DFA. Then we find the transaction for the input symbol. So what is in Q0 of 0? So Q0 of 0, we get Q1. So only one transaction, only Q1. So now we get a new set of states, Q1. So it is named as a capital A. Here, this capital A is a new state of DFA. Okay, already we get Q0 is a starting state of DFA. Then now we get the capital A is a new state, another one state of DFA. So like that, find the transactions for the input symbol 1 in the starting state is Q0. Now we get it as two possible transactions, Q0 and Q1. So the transaction Q0 to 1 is moved to the self loop and also moved to Q1. So two states. So now we get different set of states compared to the A. So we can give new name for this set of states, that's an B. Then we find the transactions for the symbol capital A. So next state. So that's why it has only Q1. So Q1 state has transactions. For the input 0 is Q0 and Q2. So that is a new set of states. So we give the another name, that is in C. So this transaction function is calculated up to until no new set of states creations until, okay. So if new states are created means we have to find the transition function. So for that states, okay, no more state creations. That is an our end. So Q1 of one transactions, no transactions. That is an empty. Then the next stage is our state B. So it has two symbols, two states in the B, Q0 and Q1. So for that, for the 0 transaction, find the transaction of Q0 and 0 and find transaction of Q1 and 0 separately and check the union. Okay, now we get it to different set of states, Q0, Q1, Q2. So I give another name for the new state in the DFA, that is an D. Then B is calculated in the same way for the input symbol 1 and C is the next state. So it has Q0 and Q2. So find the transactions of the 0 from the state Q0 and Q2. Q0 has Q1. Then but Q2 doesn't have any translation for the input symbol. So only Q1. So these states are already defined state, that's in capital A. So I give the same name for this. If newly created state means we give the new name. So in this same way, the one transactions, then the finally the D is in the last state. It also has the transactions D is the same state, that's in self loop. And for the transactions of input symbol 1, it has B. So no more new states are created. We find all transactions for the input symbol for newly created states. So we have Q0 is the first state, then A second state, B third state, C is in fourth state, then D, totally 5 states for the DFA. So it is a state table, that's a transition table for the DFA. So here the each and every set, subsets of the states are described in the first table. In the second table, the A common name is given. So here, the Q0, in this initially, Q0 has arrow. So in this table, this arrow is indicated Q0 is a starting state of the DFA. Then the other states A, B, D are as star. This star symbol is indicated. These states are final state or acceptance state. That means which are final state? So the final state of NFA is Q2. So this, the final or acceptance states of NFA is Q1. So this Q1 is a subset of the capital A and capital B, Q0, Q1, okay, capital B and capital D. So we take the A, B, D are a final acceptance states. So C is an substates. Okay, it doesn't have a acceptance state. So it has 3 acceptance states, A, B, D, like that. Then the transition function is described by the transition diagram. So here Q0 is a starting state. It's indicated by this arrow. Then for the input 0, it moves to A. So in this transition function, the acceptance or final state is indicated by the double circle. So here A, B and D are a final state. So that can be represented by the double circle. The initial state is indicated by the arrow. So this is a transition diagram. So how to draw the transition diagram? Q0 has a transitions to A for the input 0. So it is moved to 0. Then it is moved to B state for the input 1. So based on the input, how the states are changed, that to be described in the transition diagram. So in this next A, it moves C for the input 0 and no more transition for the input symbol 1. So it is a transition. So no transition like that. A and D. So this is a transition diagram. So for the minimum DFA, so it is an actual DFA, from that we can minimize by the equivalent. So here, basic conditions for minimization. Basic conditions for minimization is it cannot compare the acceptance state of the final state with any other period state of the starting state. It can compare only the final states within that, cannot come to the comparisons to the first state or any other state, starting state. So here in this transaction, Q0 and C have the same transaction. Q0, A and capital B for the input 0s and 1. In the same way, C is also have A and B for the input 0 and 1. So we can equalize Q0 and C. So for that, instead of C, we can use Q0 because in this Q0 and C is an equal. So we have to remove C state, then take the first state in the ordering. So we have to take the first state, that's in Q0. So wherever the C transactions is available, so we have to replace by Q0. Here, it has C transactions. So in this A, for the input 0, it moves to C. So that can be changed as Q0 after the equalization. So next, here, 3 states, acceptance states A, B, D. Here, B and D have a same transaction for the input symbol. So we can equalize B and D. Now we get the transition table S with the 3 states Q0, A, D. Okay. So next, the transition diagram for the transition table is, so here Q0 is the starting state, then it has the movement for the next state. The next state is A, then other state is D. Only 3 states are available because B and D is equal. So we remove the D state, then only we have the D state. Okay, then so 3 states are available. Then for the input 0, it moves to A. Then for the input 1, it moves to D. Then from the state A, for the input 0, it moves to Q naught. Then no more transition for 1. Then B, it has self loop for the inputs 0s and 1s. This is a transition diagram. It is a minimized DFA diagram. So the next method, that's all. So next method, conversion of NFA to DFA using subset construction method. So there is a second method. So here it has the following steps. We first construct NFA with epsilon from the regular expressions. So here that can be performed by Thomson rule. And NFA epsilon to DFA conversions is the second step. Then minimized DFA. So how to convert the NFA to, there's a regular expressions to NFA with epsilon by the Thomson rule. Initially, the basic concepts in the Thomson's construction. Consider epsilon is the one transaction, so it can be derived or expressed by the starting state is an I. Then it has only one transaction, epsilon. Then the F is an final state indicated by the double circle. So epsilon here, no more transaction, no more input symbol to be transferred. So here only the connectivity. So move from this state to another state. That's all. That's an epsilon transaction. If the input symbol is A means, so for the input A from the first state I to move to the F. That's an acceptance stage. Then for the input symbol A/B. So consider A/B. So that means it is generate only one. It can generate only one length string, but two strings A or B. That's an A/B. A/B means it generates A or B. Okay, but the string length is only one. So it has two possibilities from the starting state for the A/B. It also represented by A plus B. Okay, so here the starting state is 1. Then from this epsilon turn, so first draw for A, there's a 2 to 3, and draw for the B 4 to 5. Then these two sub-state diagrams are connected with the first state and last state with the epsilon transaction. So from it has two possible of transaction from the state 1, 2, 3, 6 for the input symbol A, otherwise 1, 4, 5, 6 for the input symbol B. The next example, AB. So here AB. So this automata only accepts for the substring AB. One simple string, that is an AB. So A must be followed by the B. So the starting state is 1. So next, if the starting state 1 have A input means then only move to the second state. And the second state must have input B, then only it moves to the third state. That is the final state. So it is an NFA for the AB string. So if A star, then how to write A star? So A star means 0 or more. So no more transactions, no more data transactions is possible, but it can accept for the empty transaction. So here, so the first one is a starting state. From the starting state to 1 epsilon directly move to the final stage. So epsilon is also possible in the A star. So it's the first one, first string, okay, generated by A star. Then second one, what are the strings generated by the A star? Epsilon, A, comma, AA, or AA, like that. Okay, 1A, 2A, 3A, 4A. But first one is epsilon. So that can be indicated by this, the first state to last state epsilon transaction. Then the second single A. So 1 to 2, then 2 to 3, then 3 to 4. So based on this Thomson rule, we must construct and draw the NFA by this way. Okay. So this is a single A transaction. If 2A means From the 3, it has one backward epsilon transaction. Only move from one state to another state without input symbol. Then again 2 to 3, another input symbol. Then another backward, then another. So for the number of A, it can be moved backward. This is A star. FA. So for that, first step, construct a NFA with epsilon by using Thomson construction. So in this view, we have A slash B only. Okay. So this is an A slash B. So the for the A slash B, the transactions 1, 2, 3, 6 are 1, 4, 5, 6 like that. Then what is in star? We have to add one more state, the left and right. Okay, one backward epsilon transaction and one forward epsilon transactions from the starting stage. Okay, so that is an A slash B, the whole star. Then A, B, B are concatenated. A transaction, B transaction, and another one B transactions are concatenated with this state diagram. So that is described by in this format. So here the 0 is a starting state. There's an indication of this arrow. Okay. So from this to 0 to 7 is an A slash B, the whole star. And A and B is connected. So here the final 10 is in last state. It is indicated by the double circles. So the number is not a specific format. We can give anyone in the different way also. Sometimes we can give Q0, Q1 like that. It is in each state. So represent in any way, A, B, C, D like that. Any format we can represent. So it is not my. So we want to start from 1 also. Okay. So this is not a problem. So it is an NFA with epsilon. Then we are going to convert NFA to DFA. For that, what is the first state of DFA? The epsilon closure of starting stage of NFA is called as starting state of DFA. Epsilon closure of first state. What is an epsilon closure? The continuous epsilon transactions from that state is called as epsilon closure. So we can say here the 0 is in one state. So what is an epsilon closure? So from the 0, it has the epsilon transaction 1. Okay, so epsilon closure of 0 is 0. Then it has epsilon transaction is 1. Then 1 has a continuous transaction 2. So 2. But next one is A. So now this way is stopped. Then move back. Here the 1 has one more transactions for the epsilon in the another direction. That is in 4. At the same time, the 0 has one more epsilon transactions that is moved to 7. So like that we can take. So consider 8 is in one state. So what is an epsilon transactions for 8? No more epsilon transactions here. So we consider only 8 is an epsilon closure of 8. Epsilon closure of 9 is only 9. So no more epsilon transaction like that. Okay. So first epsilon closure of the starting state, that is in 0, is 0. Then it is 0, then 1, 2, 4, then 0 to 7. These states are. So here 0, 1, 2, 4, 7. So it is named as the capital A. So this capital is a new state of DFA. So then find the transition for the input symbol A and B. So here del of capital A comma A. So here the capital A has 0, 1, 2, 4, 7. Here the 2 has a transition of A that moves to 3. At the same time 7 is also have a transition A. So del of capital A comma small a is 3 comma H because it has 5 sub-states 0, 1, 2, 4, 7. But the 2 only has a transaction. 7 only has a transaction. So we take what is the target of that a transaction? That is 3 and 8. So we take only 3 and 8. So then find the epsilon closure of 3 and 8. So epsilon closure of 3 is first take 3, then it has epsilon transactions to 6, then it moves to 7, okay, then it does A. So stop that. So 3, 6, 7. So in the same time, 6 is also has one background epsilon transaction that moves to 1. Then one has backward, okay. Then one has a forward 1, 2 epsilon transaction and 4. So epsilon closure of 3 is 3, 6, 7 and 1, 2, 4. Okay. Then epsilon closure of 8 is 1, 8 because no more transactions for the 8. So 3, 6, 7, 1, 2, 4, 8. Rearrange this. Okay. Now it is a new set of states because A has only 5 states. That is 0, 1, 2, 4, 7. Compare that. Previously generated states. Okay. So here no more 2, there is 3, 6. Some states are added. So we give new name for this set of states. That is B. So B is a new state in the DFA. So like that we can construct or calculate the transaction functions for the state A for the input symbol B. So here B, so here the set of subsets are 0, 1, 2, 4, 7. Here only 4 has a B transactions. No other symbols. We didn't have B. So the transaction of B in the capital A is only 5. That moved to the 5. So only 5. Then the epsilon closure of 5 is 5, 6, 7. At the same time, 6 backward transaction is 1, 2, 4. Okay. In the rearranging, now get new set of states, new set of items in this collection of states. Okay. So we give new name that is in C. So we already find A, B, now it is in C. So find the transactions for the B. So B has a collection of subsets. So here 2 and 7 only have the A transaction. So the target is 3 and 8. 2 as a target is 3 for the A input. 7 as a target is 8 for the A input. So find the epsilon closure for that input symbols. For the state 3 and 8. So we get already defined set. That then B is also has the same content. So we give the new name. So this transaction function is also calculated until we get a no more new states. Okay. So then transition functions for the state capital B for the input symbol small b. So here 4 and 8 only has the transition. 4 has a target is 5, 9, 8 has a target is 9. So now then find the epsilon closure of 5 and 9 is 5, 6, 7, 1, 2, 4, 9. So it is rearranged. It is a new set of states that is in D. So next transition functions for the C for the input symbol A. It is give already defined states B like that for the transition functions of the D for the input symbol B. So it has produced a new state that is in E. So we want to find the transition for input symbol A and B for the new state E. So transition of A 2 and 7 only have A transition. So its target is bigamind like that. So already we calculators in this earlier for the transactions of the A also we can take it easily. Then E of B, it has only one transaction, that is moved to 5. So epsilon closure of 5, that is in C. That's all. Okay. So this is a transition table for the transaction functions. So A state, for the small a input, it moves to capital B, and the small input to C, it moves to the capital C. So like that. So this is a transition table. Then the transition diagram is the starting state is an A here. Okay. Then which one is acceptance state? The E is an acceptance state because the E has a collection of states where 1, 2, 4, 5, 6, 7, 10. But the 10 is an acceptance states of NFA. So that will come only in the E stage. Okay. So we take this is a acceptance state or final state of the DFA. So like that, The E is the final state. So we can draw the transition function, the transition diagram from the transition table. Okay. So for the 0, it moves to B. For 1, it moves to C, and like that. So B has a self loop for the input 0. Next, move to the minimized DFA. So in this minimization DFA, so the main point is the equalization method. Main point is we cannot compare. We can't compare. Okay. So we can't compare the acceptance state with any states, but any other states can compare the transition functions. So here the states B and C, or B and C. So here the same transaction for A and C. So A and C have the same transactions B, C for the input 0s 1. So we can equalize A and C. So remove the C. So only get the A. Okay. Then instead of C is replaced by A. Then next. That's all. Okay. So only two states are equal here. Then, so one states are reduced. So now we get only 4 states. So that's transition diagram is described here. So the A is in starting state. So then D is in final state. So others are the interior states. Final states are indicated by the double circles. So that's all. This is a minimized DFA for the given regular expression that can be converted into a NFA with epsilon. Then from that find the transition function for the DFA. Then find DFA diagram, DFA with all the possible states, then convert into the minimized DFA. The third method is direct method. So here we didn't move to the NFA. Directly we can construct a minimized DFA from a regular expression. Okay. So here basically we know the first and last position of the each symbol in the regular expressions. Then find the syntax tree. Then find follow position. Finally design a DFA. So here in the first step, I consider a regular expressions A/B the whole star. A B. So here the last symbol hash indicate the end of the step. Okay. So it is in regular expressions that is indicated. The end of the regular expression is indicated with the hash symbol. So then initially we give a number for each symbol in the regular expression. Here the first symbol is an A, so it is first number 1. Okay. The second B is in 2. Then third A is in 3, and fourth this B is in 4. Then the hash symbol is number as 5. Okay. So if you give a number based on the position, okay. So first A is in first, then second one 2, like that. So initially give number each symbols in the regular expressions. Okay. Second, find the first and last position. So here, see the syntax tree. First see the leaf, that is an A. Okay. So assume only A. Okay. Don't consider all other symbols in the regular expressions. Only consider A. So if A is in regular expressions, so what is in first symbol? That is the first symbol. So the left side of A has 1 within the square bracket. So it indicates the first of which are elements are comes in the first position. The right side the square bracket, it indicates which elements will come in the last position. Okay. So if regular expressions A, it has only one symbol, that is in A only. So the first position is 1, that symbol only. The last position is also that symbol only. So like that B, that consider only B separately. Don't concatenate with any other symbol A/B stuff, anything. Okay. Only take B. Okay. So here the first position of B is a regular expression. So what is the first position? B is a regular expression. It is possible to generate only a B. It's a string. It can generate only one string, that is an D. So this is the first position element. That B is the first position. That D is the last position. So like that, then move up here the slash. That's an A/B. So now imagine the regular expressions A slash B. Okay, A slash B. So it's possible to generate A or B. Only it is possible to generate two strings, A or B. Okay, so the first position symbols may be a 1. If it generates B only means maybe a 2. So in the same way, the last positions 1 or 2. Now, then take the next symbol, A slash B the whole star. A slash B the whole star, it is possible to generate epsilon, A or B or AA or BB or AB, BA, like that. Okay, so in this input strings, what are the possible to the first symbol? Epsilon, no more symbols. So if the symbols come means A may be a first symbol or B may be a first symbol. So in this last, A may be a last symbol, B may be a last symbol. So here for the star, the first and last symbols are 1, 2 like that. Next, dot. It's in concatenation. So next we take the one more symbol, third A. Okay. So now A slash B the whole star A. Okay. A slash B the whole star A. So clearly note that. So what is the possible strings to be generated by A slash B the whole star A? A slash B the whole star sometimes may be epsilon. So in that time A must come. A slash B the whole star A. Okay. So it's may possible the first one is an first symbol A or maybe 2. Sometimes the third A only a first symbol. But this regular expressions must ending with the 3. That is an A. Because doesn't have a epsilon, star plus anything. A. So it must this regular expressions ending with A. Okay. Now I imaginely consider up to A only in the regular expressions. Okay. The regular expressions A slash B the whole star A. So here consider up to A only. So this regular expressions must ended with A. So the last symbol only the third A, that is in 3. Then next concatenate with the B. We have to take the next symbol B. So here initially A will come, first A will come, otherwise B, that is in second number B will come, otherwise the next A, third A will come. Okay, the third A must come. Okay, so it is no more choices. But the first A and second B has a choices. So in this next concatenation, for the fourth symbol B, so the first position 1, 2, 3, the last position must be a B. At the same way, hash symbol, the first position is 1, 2, 3, the last symbol must be 5. That is an hash symbol. Okay, so this is a syntax tree for the first and last position. Then it is also table. Okay, for the state, first one is 1 and 1, last is 2 and 2. So like that. So here, the first position of root node. What is in root node? The first concatenation dot symbol, that is in root node. Okay, so this one is root node. So here, the first position of 1, 2, 3 is the starting state of the DFA. So the first position of the root node is an starting state of DFA. So it is named as capital A, 1, 2, 3. Then, so here we want to find the follow also. Okay, so first construct a follow table. So for that input symbols 1, 2, 3, 4, 5. Okay, 5 symbols are available in the regular expressions. What is the follower of 1? So the 1 followed by a 1 or 2 or 3. 3 must come. Okay, so 4 didn't follow the 1. Okay, so the follower of 1 may be a 1 because A slash B the whole star. That means A in any combination. Okay, so A, B, B, A, B, A. So like that, A, B, A or A. So the first 1 and 2 in any combination, that is star. So the follower of A is maybe 1 maybe 2, or if the B didn't come in, so in this time the follower is 3. Okay, so 3 must come. So, but we can't take the follower of this one is, we can't take 4. Okay, then the follower of 2 is, this 2 is available within the star. So, we can take the follower of B is B or A, there is a 1. Okay, so for the avoid the confusion, we give the number. Okay, the follower of 2 is maybe 1 or 2 or 3 only. Okay, no more chance for the 4. Then what is the follower of 3? Follower of 3 is the next data, only B. That's a 4, only a follower of 3. Then the follower of 4 is only 5. Follower of 5 is actually, that is a follower of 5 is null. Okay, so it is wrongly entered, not a 6. Okay, follower of 5 is null. No more symbols followed. Okay, so wrongly entered. So follower of 5 is null. Then from this follow table, we can construct the transition function. So the root, first position of root node is 1, 2, 3. It is the starting state of DFA. Okay, so the transition of A is the transition of small a or the capital A is here 1, 2, 3. 3 symbols are available. Where which are A first to find? So here the 1 is A, small a, and 3 is an small a. So we have to find follow of 1 and union of follow of 3. So from the capital A, it has 1, 2, 3. 3 symbols. Okay. For the small a transactions, which are A, the 1 has A and 3 has A. So follow of 1, union of follow of 3. Okay. Person follow of 1, 1, 2, 3. And follow of 3 is in 4. So that union is 1, 2, 3, 4. This is a new stage. Okay. So already A has 1, 2, 3 only. So we give new stage. Okay, name that's an B. Then find the transitions for the small b for the state capital A. So capital A has 1, 2, 3. Here only B has only 2. 2 has a B transition. Okay, so we find the follower 2 only. Follow of 2 is 1, 2, 3. That is in the same state, already defined state, capital A. Then the transition of small a from the capital B. So the capital B has 1, 2, 3, 4. 4 states. Okay. So here the small a is 1 and 3. Okay. So we find the follow of 1 and 3. Then take the union. So follow of 1 is 1, 2, 3. Follow of 3 is a 4. So after the union, we get B. Okay. So like that, the transition of small b is also find out. Okay. From the B, here 2 and 4. Two numbers have a symbol B. So we can take union of the 2 and follow up 2 and follow up 4. Okay. The next C, it is a new state, give a name because it has a 5. Okay. So we give a name that is an C. Then the transition of small a, the C has only 1 and 3 as a transaction, A symbol. So we take the follow. This is an B. At the same way, B for the B input symbol, the C has only 2 and 4 as B. So we can take the follow. So we get a new state C. So this is a transition table for the transition function. Okay. So only has 3 states A, B, C. Okay. So here the last stage is in C. The half simple 5 is available in which subset? So that is an acceptance state or final state.
Sorry for interruption, but your PPT is not visible. Ma'am, your PPT is not visible and you are muted also now.
Ma'am, Vallirathi ma'am, please share the PPT ma'am. Not visible to the participants. Ma'am?
Okay, sir.
Okay, ma'am. Okay, ma'am.
Hmm. Hmm.
Okay, ma'am. Now visible, ma'am. You can continue.
Ah,
Thank
okay.
you.
So, on minute, on minute, wait, share this. Share. Ah, okay, sir. Sir, okay, sir. Now you can visible. Like,
Well, not visible, ma'am.
ah,
Now visible. Now visible.
It's
You
coming,
can.
ma'am. Yes, it's now.
okay. Now, now in the state of state table constructions. Okay, now in the stage of table constructions. Okay, okay. Here the final state isn't C. So how it is marked as a final state? The hash number 5 is available in the item C. Okay, so now the C is an acceptance state, then A is an starting state. Next, the transition diagram. Okay, for this DFA. So it is from this direct method, we can get minimized DFA directly. Okay, so we have three states, A, B, C. So here A is in starting state, then B and C is in final state. Then the transition functions. For the A, it moves to B. For the input symbol B, it is in the self loop. Like that, B for the input B, it moves to C. For the A, it is in the self loop. The C move to B and the self loop for the input B. Okay, that's all. This is a minimized DFA. This is a direct method. So it is very useful and we can directly convert to the minimized DFA. There's a time consumptions and everything to be it's very efficient compared to that all other method. Okay, so because the limit storage and efficiency, the time consumptions to be carried out here. So this is the third method. So that's all. So in this session, we studied or discussed about three methods. That the regular transition functions. Okay, so here the NFA without epsilon to DFA and NFA with epsilon to DFA by using Thomson method and the subset model. Then finally direct method. It's an directly convert from the regular expressions to DFA. Okay, so that's all. So this is a conversion method. Okay, thank you. Any queries? You can ask.
Ma'am, if you don't mind, can you share this PPT with us?
Yes.
Yeah, please. Thank you so much, ma'am.
Please. We will send you the PPT on later, ma'am.
Yes, sure, sir.
Sure, sir.
Thank you, ma'am. Thank you.
Any other queries?
No.
Okay.
Thank you so much, ma'am, for your informative, engaging session. Before we conclude today's session, I kindly request all participants to please take a moment to fill out the feedback form, which can be found in the chat box. Your feedback response will serve as confirmation of your attendance today and is required for certificate issuance at the end of the program. I hope that all the participants understood very clearly on today's topic through presentation. Thank you. Finally, I invite Mr. LPA Princely, HOD, Department of Computer Science, JP College of Engineering, will deliver the vote of thanks. Please, sir.
Good evening, everyone. I would like to thank our chairman, Reverend Father J. Arulraj, and our SDM administrator, Reverend Sister Hamlet, for their guidance and support to our department activities. And I also like to express our sincere gratitude to our principal, Dr. M. Rajkumar, for this encouragement and backing throughout this initiative. And I extend my special thank you to our distinguished guest speaker, Dr. I. Vallirathi, Associate Professor from Rohini College of Engineering, for sharing your expertise and insights with us. Your session was informative, engaging, and thought-provoking, ma'am. Thank you so much. And we appreciate our participants through Google Meet and YouTube Live for active engagement and enthusiasm throughout the program. And your participation and feedback have been invaluable in making this program a success. And last but not least, I would like to thank our organizing committee and all staff members who work tirelessly behind the scenes to ensure the success of this program. Once again, thank you all for this making this first faculty development program a memorable and enriching experience. We look forward to your continued support and collaboration in our future endeavors. Thank you all.
Thank you for expressing our gratitude to all involved. We look forward to seeing you all at tomorrow's session. Please ensure you arrive on time. Once again, thank you all for your participation. Hope you have a wonderful time at the today's program. Thank you all.
Thank you, sir.
Thank you so much, sir.
Thanks.
Thank you so much, ma'am, for your insights.
Thank you.